We're going to move on and look at the bisector method. And the bisector method is going to be a little more efficient than the previous method, the incremental search method. And so what we're going to be doing is we're going to be guessing a lower and an upper bound. So we still have a bracketed method. But what we're going to do is we're going to guess a lower bound and an upper bound for the zero. And then we're going to take the midpoint of that bound. And what's going to happen is that midpoint may be closer to the actual zero. And so we're just basically going to keep repeating that process to where the midpoint is going to replace one of the endpoints in the interval. And we're just going to keep repeating that until we get to a really narrow interval and we get a really good guess with respect to what our midpoint is going to be. And the midpoint is going to replace the approximation each time. So let's call XL the lower guess, and let's call XU the upper guess. And the interval where we're guessing the zero lies is on the interval XL to XU. The bisector method basically says that first we're going to graph the function. We're going to make sure it's continuous, because if it's not continuous, then we can't necessarily use the bisector method over that given interval. And then we're just going to approximate a lower and an upper bound. Then what we're going to do is we're going to find the midpoint. Okay, so we're just going to take the average of those 2 points. And then this is really the charm of the algorithm. It's pretty simplistic. If the lower bound and the midpoint, okay, so I'm calling XR to be the midpoint, if they have different signs, then we're going to replace the upper bound with the midpoint. And then if they have the same signs, then we're going to let the lower bound replace we're going to replace the lower bound with the midpoint, right? And what we're going to do is we're just going to keep doing that until we hit a specific error. Right? Now, this method should be, in general, a little more efficient, although on occasion we can just get lucky and the incremental search method might be a little faster. Okay. However, the algorithm's a little bit tougher. All right. So here's a depiction of this. And so what we do is we have a zero. Okay. So let's just guess that we have this function. It's a continuous function. And let's guess 50, and let's guess over here is m. So this would be like the lower bound, and then the upper bound would be m. And then the midpoint would be somewhere between those two values. Well, notice that the midpoint has the same sign as the lower bound. They're both the midpoint and the lower bound are both less than zero. Okay, so this would be the function at the midpoint. This would be the function at the lower bound. And so what we do is we replace the lower bound with the midpoint. Then we take the midpoint again. Okay, and we can clearly see that if this is the midpoint now, and right here might be the function at the midpoint, then the function at the midpoint has a different sign than the lower bound. Okay, so notice that the function at the midpoint right here is above zero, right? And then down here, it's less than zero. And we just keep repeating that process until we keep narrowing it down, the interval. Now, I'm going to ask folks to be able to code this for one of the assignments, okay? So I'm not going to show you the actual code, but one of the things that may help you before you actually code one of these is to be able to just do it by hand and see what happens, right? And that's what I'm going to do in this video is I'm just going to go ahead and show you the method by hand so that way you can kind of see what's going on with it. And usually if you can see it, then what you can do is code it fairly easily from there. So let's take a look at this function. We have f of x equals e to the x minus 3. All right, it's a pretty preliminary function. I think we used it in the last example. And so we're going to write MATLAB code just to plot it and approximate the lower bound and upper bound. And then we're just going to do 2 iterations of the bisector method, just so we can see how this works by hand. And then what you might want to do is just code this. Now, the next numerical method I'm going to do, I'm going to work through all the code of that one so you can see the process. But since this is going to be more for an assignment problem, I'm not going to actually do the code for this one. All right, so first things first, let's go ahead and code this and get an approximation for the upper and the lower bound. All right, so I'm going to clear all as usual, and I'm going to say sims of x, and let's let our function f be equal to exp of x minus 3. And then I'm just going to easy plot f. And what I'm also going to do is I'm going to turn the grid on. All right, we always want to make sure that the grid is on when we do this. Let me just check just to make sure I have the right function here. E to the x minus 3, I do. So let me go ahead and run this. And if I do, I'll get a pretty simplistic graph. We know it's a continuous function, right? So we're not worried about that too much. And I probably should guess that the zero is like right here. So maybe something like, if I was to really guess where the zero is going to be, maybe between like 0 and 2, it looks like. Although if I zoomed in on the graph a little bit, I could probably get a better approximation. All right, maybe between 1 and 2 might be better. All right, clearly it looks like 1.5 is just about going to be the zero, right? So let me show you what would happen if we were to employ the bisector method. All right, so I'm just going to go ahead and share my whiteboard just so I can show you a few of these iterations, etc. All right, and then it might have gone off the screen. I don't know, but I'm just going to share it again just to make sure it's on there. Okay, so first things first, we know that the interval that we're interested in is going to be 1 to 2. All right, so that's going to be our guesses for this. All right, that should be the first thing that we always do is we look at the graph and we just figure out what our guesses are going to be for that interval. All right, now from there, what we need to do is we need to figure out what f at 1 is, and then we need to figure out what f at 2 is, because we need to figure out what the signs are for this. Okay, and remember our function, I'm just going to write that over here, f of x was e to the x minus 3. Right, and so f at 1, and just to show you how I'm getting that, e to the first minus 1 minus 3. Okay, and I computed this beforehand just for efficacy of this. That's like negative 1.2 approximately, negative 1.28172. And then f at 2 would be e squared minus 2 minus 3. All right, and that works out to be 2.384. And we really don't care about too much else other than sign. Okay, 056. Now I need the midpoint. Okay, so I'm calling this like iteration 1. So if this is iteration 1, all right, then our midpoint would be 1 plus 2 divided by 2, which we know is going to be 1.5. And I need to figure out what f at 1.5 is. Okay, and that would just be e to the 1.5 minus 1.5 minus 3. Right, and when I compute that, now remember on our graph when we did this, it was really close to the to the 0, and that would be negative 0.01831 approximately. Okay, and I want you to notice that because the low has the same sign. Okay, so this is the low, right, and this is the upper. Okay, and so we note that the low has the same sign as the midpoint. Okay, so what we're going to do is we're going to replace the low with the mid. So now the low is equal to the midpoint. Okay, now this is our current guess. Okay, so this is our current guess as to what the solution is, or the 0. All right, so now with iteration 2, now my interval, the low is now the mid, so my interval now is 1.5 comma 2. Okay, so now the low becomes 1.5, and then the upper bound stays the upper bound. Okay? Now for iteration 2, we already know f at 1.5, okay, that's approximately negative 0.018131. We know f at 2, right? So f at 2 was that 2.384056, okay? It should be a 0. I don't know what character that is. And now we need to find the midpoint, okay? So we're going to take 1.5 plus 2 divided by 2. That's 1.75. All right, so now we know that we have to find f at 1.75. Okay, and that's going to be equal to e to the 1.75 minus 1.75 minus 3. And then when I compute that, I get 1.00, and we could probably stop there because we know what the outcome is going to be, but 4603. Now, I want you to notice that that is a different sign than the lower bound. Okay, so low has a different sign than the midpoint, right? So now the high is going to be equal to the mid, all right? And so now our interval is going to be 1.5 comma 1.75. All right. And I want you to notice that we're narrowing down the interval. Okay. If I were to do this another 5 or 6 times, right, then what I would do is I would get to a very narrow interval. All right. And that's what the bisector method does. All right. So hopefully that helps you. And when you go to code this, you're going to need a while loop. But what you usually do with numerical methods is you just do the numerical method once outside of a loop. And then once you've done it once outside of a loop, then you just go ahead and cut and paste that algorithm and put it inside the loop. Okay. So usually we're going to do the first iteration outside the loop. Okay. Then what you do is you make sure it works. And then what you want to do is inside your while loop, and you want to make sure that the error, so while the error is greater than some sort of user error, okay, that's where you're going to do all the exact same algorithm and put it inside of your loop. All right. And hopefully that helps. All right. Another thing you should probably do is before you do the first iteration, you should probably set up like some sort of table as well. So for instance, you might have like the iteration number, and then you might have like the lower bound and the upper bound and then the midpoint. And then you might have like your error after that. You always want to make sure that you just do your table, your header. If you're asked to do something like that, you want to make sure that you do it outside of the loop, and you actually want to do it before the first iteration. All right. So in the last video in this, or the last two videos, what I'm going to do is I'm going to outline something called the false position method. And then once I outline it, I'm going to show you the code as to how to go through and program that using MATLAB.